Good afternoon, everyone. Welcome to the third day Faculty Development Program on Recent Trends in Materials and Flexible Electronics. So today our lecture will be spoken by Dr. Mitradeep Bhattacharya. He did his master's and doctorate from IIT Guwahati, and he's a postdoctoral fellow of University of Glasgow, UK. Currently, he is working as an assistant professor at IISER Bhopal. Sir, you can join us. Am I audible?
Yes, yes. Thank you, Kanchak, for this introduction. So, should I start?
Yes, yes, you can start.
Okay. So I'll share my presentation. Just a minute. Wait. So my slide is visible now?
Sir, this is visible.
Okay, okay. Thank you. So,
Yes, it's visible.
okay, thank you. Just a minute. Okay, so today my topic of discussion is flexible electronic sensors and systems for healthcare applications. So I'd like to thank the organizers for giving me this opportunity for discussing research or say the basics related to flexible electronic sensors. My name is Mitradi Bhattacharya. I'm an assistant professor at Electrical Engineering and Computer Science in Indian Institute of Science Education and Research, Bhopal. So my research topic is also related to flexible electronic sensors and systems, especially for healthcare applications. So it's quite a long presentation, 2 hours presentation. So I guess I'll be able to keep you engaged with this presentation. In any of these slides, if you feel like asking some questions, you can raise your hand and unmute yourself for the questions. And in the middle also, if you want me to stop for something, let me know. Okay. So the topic of today's discussion is flexible electronic sensors and systems for healthcare applications. Just a minute. Yeah, so outline of the presentation is given here. So I'll start with basics of sensors and sensor parameters. And then I'll discuss why sensors are important in healthcare. Then I'll move to microstructure assisted flexible pressure sensor, which is to some extent a research based problem that I have recently developed. I'll briefly mention that so that you get a better idea about how we can develop different flexible electronic sensors. And at the end, there are different examples of sensors or sensor systems that I've developed at various stages of my research. I'll quickly go through them if time permits. And finally, I'll conclude. Now, broadly speaking, this particular presentation will have two different parts. The first part is related to the basics of sensors and different sensor parameters, how they are important for different applications. And the second part of this presentation is related to different research uh, problems or research areas associated with sensors. Um, if you think about sensors, then you'll be able to understand that it's not only healthcare. Sensors are usually used for many of the other applications, for example, say uh, environmental, agricultural, and so on and so forth. But today's discussion will be focusing on healthcare related issues. Before I start, this is IISER Bhopal. I'm a faculty member of IISER Bhopal, so I'm just starting with some of the images of the institute. It's in the central India. Currently it has uh, three different engineering branches. Why I'm highlighting this one, because ISERs are known for natural sciences. Obviously, it has natural science branches like physics, chemistry, biology, and this is the only ISER that has engineering sciences. We have electrical engineering and computer science. We have data science and engineering and chemical engineering. The flagship program of ISERs is BSMS. So we offer BSMS in electrical engineering and computer science, BS in electrical engineering and computer science. BS is equivalent to BTech. And then we also offer PhD program in electrical engineering, computer science in our department. In fact, in all the departments, all these three programs are running. So with this brief introduction about this institute, I'll start my presentation. So let us start with sensor basics. So we will first discuss what is a sensor, and then I'll discuss different types and classification associated with sensors, and what are different sensor technologies. Then I'll discuss basics of system integration. So 2 hours is not sufficient to discuss everything about sensors, but I'll try to cover most of the aspect related to sensors, especially flexible sensors. In the middle, if you have any queries, as I've told, you can raise your hand, or I may not look into the audience panel. So what you can do is you can unmute yourself and ask queries if you have any. And if I'm crossing the time, please remind me anytime in the middle. I may not be able to check the time. So just remind me if there is any time issues associated with this presentation. So let us start with what is a sensor and what is a transducer. Usually sensor, transducer, they are very closely related term. If I first describe sensor in general terms, a device that is able to respond and measure physical or chemical parameters in the environment and can translate the same into readable format or signal is known as sensor. So the basic uh, job of a sensor is to detect or measure some physical or chemical parameters in the environment, and then it will translate that particular parameter into a readable format or signal. In case of electronic sensors, the readable format or signal is electrical signal. You may find sensors which directly don't translate the physical parameter into electrical signal, and in that case, it may translate the sensor the parameter into some other readable formats. For example, say optical signal, or so on and so forth. I mean, optical, it can be optical, it can be some other form of energy, but it has to be something which is readable, either quantitatively or qualitatively. So quantitatively meaning either it will give you some numbers. If you are, say, measuring temperature of the environment, what you may expect from the sensor is to detect the temperature, then convert it to, say, an electrical signal, and then that electrical signal will be further processed to give you a readable format or readable signal where you can see what is the temperature. You should get the number. So this is one way of presenting the data or the physical parameter. The other way could be, for example, if you want to measure whether the room temperature is more than 30 degrees centigrade or 35 degrees centigrade or not in certain application. So the sensor can provide you that information only. The moment the temperature of that room, say, goes beyond 30 degrees centigrade, then the sensor will provide you certain sort of signal. It can be optical, it can be acoustic, for example, buzzer and etc., whatever it is. So that is called qualitative data. So you don't have any quantitative analysis as such in this case, but you get a qualitative analysis. Then we also have another way of measurement where you actually divide the entire range in different formats. For example, if the temperature is between, say, 20 to 30 degrees centigrade, you call it low temperature. If it is 30 to 50 degrees centigrade, you call it moderate temperature. If it's beyond 50 degrees centigrade, then it's a high temperature. In this case, it's neither quantitative nor absolutely qualitative. So in that case, you have different ranges associated with this measurement. This is known as semi-qualitative or semi-quantitative. Better to say semi-quantitative because that is the term that you may come across in different references. So you may also get semi-quantitative data wherein you will have say 3 different LEDs, and then if the temperature is say between say 10 to or 20 to 30 degrees centigrade, some LED or indication will come. If it is beyond 20, some other indication will come up to 30 or up to 50. If it is beyond that, then maybe some signal like red light or something will come up. So it's like semi-quantitative. At the same time, you have another term which is known as transducer. So a transducer is a device that is able to convert one form of energy to other. So in transducers, you may find that the device is converting, say, heat energy into electrical energy, but there is no constraint as far as the readability of that signal is concerned. So as long as the device is converting one form of energy to the other, it's a transducer. But if you look at the sensor, you'll find the sensor also is doing the same thing. I mean, it actually converts, say, one physical parameter to some other form of energy, one physical energy to other form of energy. For example, let's take an example of temperature sensor. Then the temperature sensor will first measure the heat energy, and then that sensor will convert that heat energy to, say, electrical energy. So there is a transduction associated with that. So that heat energy will first get converted to electrical energy. That is the transducer effect. But sensor has an additional responsibility. When it is converted to electrical energy, that particular signal has to be readable. So that electrical energy then should be processed and should provide you a readable signal or readable format so that you can understand is the amount of the heat energy associated with this sensor measure. So each sensor has a transducer effect associated with it. Sensor effect starts with a transduction and then slowly converts to a measurement. So that is the difference between sensor and transducer. So if I explain it schematically, for example, you have a block. Now on the left side, at the input side, you have different physical and chemical parameters. So it can be temperature, it can be humidity, this can be strain, pH, concentration of any material, etc. Then this particular block will convert all these energies into a different form of energy, and then in the output you may find that the different form of energy is either electrical or optical or any form of measurable energy or quantity. This can be voltage, this can be current, or this also can be change in color. So one of the sensor that you may come across or you already have seen, which is not an electrical sensor, is like a litmus paper. So when you have a litmus paper, you dip it into a solution. Now, based on the pH, the color of the litmus paper will change. So that is something providing that particular system or that particular device is actually providing you certain sort of information, but not in terms of electrical energy. It's like optical energy. So then you can match the color that you have received from the sensor, and with a reference that has already been provided with the sensor, then you can understand whether it's pH 7, pH 6, pH 4, or whatever it is. So this is the difference between sensor and transducer. Now, similarly, you'll find the various types of sensors in human bodies as well. So human body consists of these 5 organs that interact with the outer world. So we have eye, we have ear, we have nose, we have tongue, and we have skin. We call it Ghanendriya. So these are the 5 different sensors that interacts with the external world. And each of these organs actually can be termed as a sensor because they are basically converting one form of energy to other and then giving you some sort of readable form of energy that is processed by brain later. So these are the 5 different sensors that we have, and currently maybe in the research you'll find that people are trying to mimic all those sensors so that they also can make artificial organs. Now, the purpose of making artificial organ can be various. For example, if you have an artificial organ, you can integrate the same thing with a robot, and then the robot also can perform similar things that a human body can perform, or you can make those artificial organs to replace one of our damaged organs, if at all it's possible. So there are different transplant also. Nowadays in healthcare, you'll find that people are transplanting kidney, heart, and so on and so forth. So the idea is whether we can develop something artificially and then replace a damaged organ with an artificial organ so that the person can, or we can save the life of a person. Okay. Apart from that, there are more sensors that are there in our body that perform highly complex tasks. For example, hunger, sneezing, fever, pain, all these symptoms or all these activities are associated with some sensing mechanism. So when you feel hungry, there must be some sensor in your stomach that sends that signal to your brain that currently the stomach is empty and you or the person needs to eat something. So it's kind of a very complex biochemical process that goes in our body, and that helps us in actually identifying various symptoms associated with various tasks. Okay, so this is kind of an example of natural sensors, and if you look at all those sensors very closely, you'll find that the specification of these sensors are really, really high. For example, if you consider eye, then if I'm not wrong, the resolution of human eye is around, say, 530 megapixel or so, which is way beyond what we have currently in our digital cameras. And you yourself can understand when you see something, the clarity is way higher than what you find in a mobile phone. So you can very easily distinguish the kind of system that a human being has, or any animal for that matter has. So nature is already developing various sensors at various levels, and one of the target of recent research is to mimic those organs so that we can develop similar sensors and can also figure out some replacement of, say, damaged organ, or we can make some robotic system which is as good as a human being. Now, sensors can be classified in various ways. So one of the classification could be physics. So in terms of physics, you'll find there are various types of sensors. The sensor can be mechanical. Mechanical meaning, for example, a pressure sensor or a sensor that is converting any sort of mechanical energy into, say, an electrical energy. Then we call it a mechanical sensor. Just to make things clear, in this particular presentation, we will be discussing mostly electronic sensors. So one target of the sensors that I'll be discussing in this particular presentation is to convert the physical, chemical, whatever parameter into electrical signals, because the sensors are under consideration is an electronic sensor. So uh, one may ask that why we always try to convert things into electrical signal or electronic signal. The answer is you have nowadays a lot of electronic components that are actually capable of handling electronic signals. And once you have an electrical signal as an output, you can play around with this signal just by making different circuits. If you want to amplify it, you have amplifiers. If you want to remove certain frequency from that signal, you have filters. If you want to convert that signal into different form of say waveform, then you have say different oscillators or waveform generators. So these aspect gives us a kind of flexibility of using electrical signal the way we want, and that is why the first and major target uh, as an say sensor or device engineer is to convert the physical parameter into electrical energy. So as I was saying, that the sensors can be divided into various forms. So the first one is mechanical. That means you convert, say, mechanical energy into electrical energy. Then we have electrochemical sensors where you convert, say, a chemical energy into an electrical energy. Then we have electromechanical sensor. Electromechanical sensor meaning when you have a mechanical process involved with an electrical process. For example, say you have accelerometers. So accelerometer is something that is an electrochemical sensor, and in that case, what usually people do is like they develop a kind of capacitive structure which has a kind of movable part, and then when you put that entire system into acceleration, that movable part will deflect from its original position. And if there is a deflection between two plates, then the capacitance also will change. Now that change in capacitance can be calibrated with the acceleration. So this is kind of an electromechanical sensor where you have a mechanical motion associated with an electrical response. Then you have capacitive sensor where the output will be in the form of capacitance. You have inductive sensors where the output will be in the form of inductance. Similarly, you have optical, thermal, magnetic, microfluidic, piezoelectric sensors. So these are the classification based on physics. Then you also can, classify sensors in terms of various devices. So a sensor can be FET based sensor, that means field effect transistors. This also can be a MOSFET based sensor, that is metal oxide semiconductor field effect transistors. Then the sensor can be a MOS device, metal oxide semiconductor. The sensor can be a MEMS or an EMS device, that is micro electromechanical system or nano electromechanical system. So once you have a device, electronic device for that matter, for example, if you have a FET which can detect, say, a certain sort of chemical, say this can that particular FET can detect, say, oxygen or say hydrogen, then in that case the sensor is an hydrogen sensor, but it's again a FET based sensor because the sensor functioning is based on a predefined device, that is field effect transistor. Then you can also classify the sensor in terms of application. So the sensor can be physical sensor, chemical sensor, biosensor, biomedical sensor, or environmental sensor. So if a sensor is performing a chemical detection, we call it chemical sensor. If it is detecting something related to bio sample, we can call it biosensor. If the sensor is also associated with some biomedical application, for example, this is a say blood pressure sensor or blood glucose sensor, in that case these are a biomedical sensor. However, a blood glucose sensor can also be termed as a biosensor because blood glucose is again a biological parameter that you are sensing. So a biomedical sensor can be a biosensor as well. Then it can be an environmental sensor if you are detecting some environmental parameter. For example, say if you are detecting humidity, relative humidity, or say the concentration of carbon dioxide present in the air. So in that case, you can term it as a environmental sensor. So these are application specific classification. Then you can classify the sensor in terms of the substrate that you use. If the sensor is made on a flexible substrate, we call it flexible sensor. If it is made on a wearable substrate, then we call it wearable sensor. If it is made on a rigid substrate, say silicon wafer, glass slide, or similar material, then we can call it a rigid sensor. As far as the dimensions are concerned, you also can classify them based on that. If one of the active dimension of your sensor is in the nanometer domain, we can call it nanosensor. And similarly, if one of the active dimension of the sensor is in micro domain, we can call it microsensor. Then based on material also you can classify sensors. So if the sensor active material or substrate material is silicon, you can call it silicon sensor. If the material is polymer, you can call it polymer sensor. If it is metal oxide, you can call it metal oxide sensor. Or you can also call it carbon based sensor if the active material or substrate material is made of carbon. Then based on states also you can classify. If the sensor is based on solid state device, then it's a solid state sensor. If it is based on liquid state device, so you nowadays get microfluidic sensors as well. So where you take help or harness the property of fluidic environment in order to detect something. In that case, you can call it a liquid state sensor. Say if there is a droplet, if that can detect certain sort of parameter, then it's a kind of liquid state sensor because your active material itself is kind of liquid material. So if time permits, I'll give you an example of that. what is the difference between solid state and liquid state sensor. Now, we also have various terminologies associated with sensor technology. So if you want to make a sensor, you need to know all these parameters listed over here. So there are 20 odd or maybe 15 odd terminologies listed in this slide. I'll not be able to discuss all of them, but I'll briefly discuss a few of them so that you get an idea about different sensor terminologies. And all these parameters are kind of very important because when you develop sensor, you need to know what are those parameters. Otherwise, the sensor may not be applicable for certain application or whatever application you are targeting. So I'm not reading it out. It's already in the slide. So slowly I'll move towards different parameters. So I'll discuss probably accuracy, precision, calibration, sensitivity, offset in this particular lecture. So let us start with the first parameter, which is accuracy. So accuracy literally means the correctness of any system. So from the term itself, it's very clear. If you call your sensor to be very accurate, that means the correctness of the sensor is very high. So it can very easily uh, or it can detect certain parameter with higher level of correctness. Now, to explain that, I've shown you two different schematic images. So in the left hand side, you have an image where you have a sensor and it has an input and output. Say you have a relation between input and output, which is shown by this blue curve. Now, say at a certain input A1, you have a response that is shown by the red dot, which is not on top of that input output relation. To make the discussion even simpler, let us take an example of temperature sensor. So in this case, you have a temperature sensor input output relationship, which is linear in nature. We call it actual curve in here. Okay, later we will see what we can term this particular curve as. But in here, let us consider that this particular curve is the actual curve. That is the relation between input and output. What does that mean? Say if your temperature is A1, then you should get a response somewhere here where the cursor is. But during measurement, you figured out that the response that you get from this sensor is somewhere here, which is on top of this curve, which is actually outside this curve, right? But this particular value, this particular output value is corresponding to the value A2. Say you are measuring 50 degrees centigrade, you get an output here, but as per your sensor curve, you should get here. Because you got an output now here in the red dot, the corresponding input value to this red dot is now A2, which is 55 degrees centigrade, for example. So you are measuring 50 degrees centigrade, but if you follow the actual curve, the system will give you a response of 55 degrees centigrade. Then this difference is known as inaccuracy. So accuracy is basically a measurement of inaccuracy. So you are trying to figure out what is the inaccuracy present in your sensor. So that is what accuracy is all about. If your sensor is very accurate or 100% accurate, you should get this red dot somewhere here on the curve. It should not be outside the curve. Okay, so that is what accuracy means. Similarly, we have another term which is known as precision. So very often you may find accuracy and precision are used interchangeably, but there is a difference between these terms. So if there is an if you do this measurement uh, uh, using this temperature sensor, you find that the response for 50 degrees centigrade, that is for A1, it is this red dot. Now what you are doing, what you have planned now is, let us take 5 different measurements with this sensor for 50 degrees centigrade, and you figured out that every time you measure, you get the output in this red dot on. That means your sensor is very precise. Although it's not accurate, it's not measuring the temperature accurately, but whatever it is measuring very precisely. That is 100% precision. Every time you measure 50 degrees centigrade, you get the output in here only, in the red dot only. That means it's very precise but not accurate. There can be another situation where every time you are measuring 50 degrees centigrade, you are getting this red dot somewhere in this curve, which is not close to the red dot. That means it's not even precise. It's not accurate and also not precise. So in that case, we call the sensor inaccurate, at the same time not precise. Okay. So if I look at the probability distribution output of my measurement, then I can define the accuracy and precision very simpler way. So precision is the probability distribution of your measurement. If the probability distribution of your measurement is very sharp, as it is shown over here, what does that mean? It means for a single input, that is this particular input, the output that you are getting is distributed as per the curve given over here. Now, if this particular curve is very steep, then the sensor is very precise. However, for this particular input, you should get an output somewhere else. For example, whatever we have discussed over here, you should get an output over here. So the accuracy is the difference between the output that you are receiving and that you should receive. And the precision is the probability distribution of your output that you are getting for n number of measurements. So that is why a sensor can be accurate but not precise. A sensor can be precise but not accurate. A sensor can be neither precise nor accurate, or a sensor can be accurate and precise both at the same time. So our target is to develop sensors which is accurate as well as precise. However, based on application, sometimes you may compromise accuracy or precision, but it depends on the application that you are targeting. For example, if you are developing a sensor for robotic surgery, it has to be highly accurate as well as highly precise. Because in case of robotic surgery, a smaller mistake or a very trivial mistake can lead to a highly complicated situation, health situation, right? So in that case, the sensor should be accurate and precise both. But if you are developing a sensor, for example, say measuring the temperature of a furnace, and in that case, you may consider or compromise the accuracy a bit or precision a bit, because if the furnace temperature is say 600 degrees centigrade and if your sensor is showing 605 degrees centigrade, that should be okay. Although it depends on the range where you are operating. If the furnace temperature is too high and the deviation from that temperature is too small, then you can use that sensor for that furnace. So it depends on the application under consideration. Okay. Another very important parameter is calibration. So calibration is nothing but the relation between input and output of a sensor. So if you have say an input which is denoted here by small s, and if you have an output which is the function of s, then the calibration curve s will be equal to that function. So in case of temperature sensor, you can consider that we already have said previously, the actual curve that we were discussing is actually the calibration curve associated with the sensor. So calibration curve is nothing but the relation, graphical representation of input versus output or output versus input. Okay, even you can uh, express that relation using mathematical equation. So a calibration curve also has a calibration function associated with it. Now, if your input and output relation is linear, we call it a linear system. If it is non-linear, we call it a non-linear system. If your temperature and the response is linearly related, then we call it a linear temperature sensor. Say if it is exponentially related, then we call it a non-linear sensor. However, a sensor can be linear in a particular range. Say between 10 to 50 degrees centigrade, the sensor response is linear. Beyond 50, it's exponential. So if you are using the sensor between 10 to 50 degrees centigrade, or your application demands, say, a measurement between 20 to 40 degrees centigrade, then you can call that sensor as linear, because anyways you are operating in that linear domain only. So that is how we define the sensors, performance, or not performance, I would say sensors calibration curve. Okay, so this particular relation is known as calibration curve, and calibration curve is very important, because without calibration curve, you will not be able to, decide the difference between, say, input and output. So it's very it's very important. And just to make the calibration curve, what you do is, once you develop the sensor, you do a lot of random experiments with a variety of inputs. For example, if you take a temperature sensor, you develop a temperature sensor, and then you put that temperature sensor in different temperature environment, from say 10 degrees centigrade to 100 degrees centigrade, and then you figure out what is the output. Then you plot that output against that input. Say if your input here is 10 degrees centigrade, this is the output. For 20 degrees centigrade, this is the output that you have got. For 30, this is the output. For 40, this is the output. And then you connect all these with a line, and then you will be able to get whether it's linear or non-linear. Sometimes it can be non-linear. In that case, you have to use a curve fitting, which is a different technique. Nowadays, you have softwares, you don't need to worry about curve fitting much, because software itself will give you the equation associated with your data plots. So that is how we actually calculate calibration. Then another important parameter associated with sensor is sensitivity. So sensitivity is something related to uh, the sensor output to the unit change of input, and that is basically the incremental change in output that corresponds to a particular input. So for any plot, any calibration curve, the sensitivity is nothing but the slope of that curve at particular point. If it is a linear curve, then anyway slope is constant, so your sensitivity is constant for that particular sensor. If it is a non-linear curve, then sensitivity may vary, because slope will vary at each and every point. So that is why one has to mention the input value in case of sensitivity calculation if the sensor output is non-linear. Because if it's a non-linear curve, for example, if you take a curve which is say changing exponentially, then at different point you have a different slope. That's why the input value for non-linear curve in case of sensitivity measurement is very important. So it's nothing but the output for unit change of input. For example, in case of temperature sensor, if it's an resistive temperature sensor, say for each degree centigrade, the change in resistance is 2%. Then your sensitivity will be 2% per degree centigrade. Okay, but it doesn't ensure that your sensor is capable of measuring 1 degree change, because this output will change by 2%, but that 2% change in output probably is not measurable by the system that you are attached with. So the system should be capable of measuring the 2% change in the output. Then only you can measure 1 degree centigrade. But as far as the sensitivity is concerned, you can report that the sensor shows a 2% change in output for each degree centigrade. Now, if somebody is willing to measure each degree change of output, he or she has to make a system which is capable of measuring that 2% change in output. Otherwise, the sensor or the sensor system may not be able to measure the change in 1 degree. Then we have another term which is known as threshold. So threshold is the minimum detectable signal. So for example, if you take a temperature sensor again, so I'm taking this example repeatedly because we all have come across certain sort of temperature sensor in our daily life. For example, if you take thermometer, digital thermometer, then it's basically a temperature sensor. So all of us probably have used digital thermometer once in our lifetime so far. That's why I'm taking the example of temperature sensor in my discussion. Now, as far as the threshold is concerned, threshold is the minimum detectable signal that your sensor can measure. Say your sensor can measure, say, 2 degrees centigrade minimum. Below 2 degrees centigrade, it's unable to measure. Then the threshold of your sensor is 2 degrees centigrade. Similarly, we have another parameter which is offset. Again, it's very important. Offset is nothing but the output of your sensor when your input is zero. That is, the stimuli is zero. If you take a temperature sensor as an example, say at room temperature. So temperature sensor actually is a tricky example as well. So we usually don't consider 0 degree centigrade measurement in case of temperature sensor. We take room temperature as zero for temperature sensor measurement, because anyways when you use the temperature sensor, you take room temperature as a reference. So say at room temperature your sensor is giving certain sort of value, we can consider this as an offset because it should show zero, but it is giving some sort of value at that particular temperature. Or to make it more clear, let us take an example of a chemical sensor, say blood glucose sensor. You develop a blood glucose sensor, and then when there is no glucose, or say a solution that you are putting that has no glucose, zero glucose, then also if your sensor gives you certain sort of signal, then it is offset. So usually we want zero offset in a sensor, but if you find that your sensor has certain sort of offset, it doesn't mean that we don't work with it. We can work with it even if your sensor is offset. But you need to then work in the system domain so that you can make that particular point as zero and then can move forward. Probably you already have seen different electrical equipment, say old multimeters, old gauge meters. There, when you start the experiment, the instrument will show you some signal. Then there is a knob, small knob, which you rotate and bring that point to zero. And then you start your measurement. So the sensor actually has a offset, or it had an offset. What you did is you forcefully made that point as zero, and then you have started your measurement. So it's something like that. Even if you have uh, a signal which is there even for zero input, what you can do is you can shift that level and then you can start your measurement. Then another important parameter is range. So range of a sensor is where you operate your sensor. For temperature sensor, this, if you are using the temperature sensor for body temperature measurement, maybe the range of the sensor could be say 20 degrees centigrade to 50 degrees centigrade, because your body temperature will lie in between that. So that is what range is all about. So each sensor will have a certain range. Beyond that range, probably your sensor data is not reliable. It doesn't mean that beyond that range your sensor is not working. Probably your sensor is working, but it's not a reliable data, or the sensor system that you are using is not calibrated for the range beyond that. So that is how you can decide the range of a sensor. Mostly you will find these type of information in different data sheets. Then we have response and recovery time. So response time is something which is associated with the measurement. For again, if you take a temperature sensor measurement, the time the sensor takes to reach 90% of the actual response from 10% is known as response time. So if response time is high, that means your sensor is performing slowly. So you, for example, say you have a temperature sensor and you want to measure a temperature of an object which is kept under 50 degrees centigrade. The moment you touch that sensor with that particular object, you are capable of getting the data in 5 seconds. Then the response time of that sensor is 5 seconds. Now, if that sensor is taking 5 minutes in order to take that data, then the response time is quite high. Okay, so usually we want the response time to be as low as possible, but it depends on the working principle and different other physical parameters. Uh, that's why all the time it's not in our control, but our target should be to have a response time as low as possible. Similarly, we have recovery time. Recovery time is the moment you take the sensor out and put it in the room temperature, how fast the sensor is going back to its initial position. So if you look at the car, initially you put the sensor and you connect it or attach the sensor with the object that is kept on 50 degrees centigrade, the response is rising. So response is rising, and then it is saturating, because at certain point your temperature is not changing, so the response also should not change. So it will saturate. So the time it takes to go from 10% of the total signal to 90% of the total signal is known as response time. That is the duration from here to here. Your x-axis is time here. Please note your x-axis in this case is time. That means it's a temporal response. Similarly, the moment you take the sensor away from the object, then your response will start falling, because now it will give you a response close to the room temperature response, but it will take some time before it reaches to the room temperature response. So the time it takes from or time it takes to reach from 90% to the 10% is the recovery time. So it also is important that your sensor recovers as fast as possible, because then only you can reuse the sensor for some other purposes, right? If it is not recovering fast, then the sensor is no longer useful for the next measurement. So that's why the target should be to have a high response time as well as a low response time and a low recovery time. Low response time and low recovery time ensures the fast performance of your device. So the speed of the device or speed of the sensor depends on response and recovery time. Then another very important parameter is drift. It's actually a very crucial parameter. So you may find that your sensor response for a certain parameter uh, decreases with time. In that case, we call the deviation as drift. Say you have a you have a temperature sensor and you want to measure the temperature of an object kept at 50 degrees centigrade. Now, the moment you put the sensor on that object, it is giving you certain output. Say here. Now, you kept that sensor here for say 4 hours. What you observed is, with time, the response is reducing. That means your sensor has a drift with time, which is not desirable. So ideally, we want zero drift sensor. However, we can also use sensors with drift if the drift is predictable. There are ways to develop the system so that you can work with a sensor that has drift. But again, it depends on various applications. Sometimes you may not consider a sensor with drift for a very sensitive application. As I've said, say robotic surgery, or say in aircraft, if there is some system that you need to monitor, in that case you will not take a risk with a sensor having drift, because these are sensitive cases. But in certain cases, you may use the sensor, because there are techniques in the system level where you can get rid of the drift if you know or predict the way the sensor is drifting. Okay. Then here I'm showing some other classification in terms of working. We call some sensors as active sensor that requires external power for operation. For example, thermistor, strain gauge. Thermistor is the simplest temperature sensor. So in those cases, you need external power to operate these sensors. These are known as active sensors. And then we have passive sensors that doesn't require power. Actually, it generates power. So for example, if you take photodiode, piezoelectric sensor, they actually generate output in terms of voltage or current. Now, in that case, we call them passive sensor, but you may find these passive sensors are also operated with external voltage or power. because the power that these sensors are generating is not sufficient to make them applicable for certain application. That's a different issue altogether. As long as they are generating external power, you can call them a passive sensor. Then we have absolute and relative sensor. For example, say thermistor. Thermistor is a temperature sensor. It's an absolute sensor. So for each degree centigrade, you have a specific value for that thermistor. That is there in the data sheet probably. If you download the data sheet of a thermistor, they'll provide you at 50 degrees centigrade what should be the resistance of that thermistor. That is provided. But there are relative sensors as well. For example, thermocouple. They work based on temperature gradient or temperature difference. Say for 10-degree temperature difference, they'll give a response of say 10%. Now, this 10-degree difference can be 20 degree to 30 degree centigrade, or this can be 40 degree to 50 degree centigrade. In both the cases, the temperature difference is 10 degree. So you will get a response, you'll get a same response for 20 degree to 30 degree and 40 degree to 50 degree. These are relative sensors. So in that case, you should have a reference for temperature measurement. Otherwise, you may end up getting a wrong result. This is the basic interface circuit details that I have given over here. So usually you connect the sensor in two different ways to the interface circuit. This can be one shown in the left circuit or the one shown in the right circuit. In the left case, say your temperature, say your sensor, not temperature sensor, any sensor for that matter. Say your sensor generates voltage. Then for better interfacing, you should know the output impedance of the sensor, and also you should use the input impedance of the sensor accordingly. If Z out is if your sensor is like generating voltage, then your Z out should be high and Z in should be low. And if the I'm sorry, if the sensor is generating voltage, then your Z out should be low, Z in should be high. Why? Because if it is generating voltage, you should get the entire voltage that is generated in the interfacing circuit in order to process it. If your Zn is high, then the entire voltage will drop against this sensor, and your Z out should be low, because whatever voltage you are generating, that should not drop in here in the Z out, right? But if it is current sensor, your Z out should be low. I repeat, if it is voltage sensor, your Z out should be high. Z out should be high, and your Z out should be low. For voltage sensor, your Z out should be low. For current sensor, your Z out should be high, because the current that the sensor is generating should go through your interface circuit. If your Z out is low, then entire current will pass through it, so it will short the sensor. So your Z out should be high in this case. If your Z out is high, then no current will flow through the Z out of the sensor. Entire or majority of the current will flow through the interface circuit. So in case of current sensor, your Z out meaning the sensor Z out should be high, so that current flowing through this particular resistance or particular impedance is very low. And the opposite is the case for voltage generating sensor. In that case, your Z out should be low. For voltage generation, the Z out should be low and your Z in should be high, because the entire voltage should come across this Z in, right? It's nothing but a voltage divider circuit. So the voltage that your sensor is generating here will drop in Z out and Z in. So if your Z in is high, maximum voltage will drop in Z in, right? And in case of current, your Z out, if your Z out is high, very small amount of current will flow through Z out. So the maximum current will flow through Z in. That is what your target is. So that is how you actually decide your interface circuit and you design your sensor impedance. So you can measure the interface circuit impedance and the sensor impedance using different electrical equipment like say LCR meter. If it is resistance, then you can simply use a multimeter. But if it's an complex impedance, then in that case you need an LCR meter to detect the sensor and interface circuit impedance. Now let us see some sensor examples. So what we'll do is I'll show some videos of sensors that maybe you already have seen, but just to give you an idea, I'll show some videos of sensors that probably will help you to get a better idea about the sensor that we use in practice. So I'll show you a temperature sensor, an optical sensor, and a humidity sensor. Okay. So this is the thermistor. This is a thermistor. A number is written over here. That is 103. So it's an 10 kilo ohm thermistor. It has two leads. Both are metal leads. And then the active material of the sensor is somewhere here in this black dot that you can see is basically the active material of the sensor. Uh, and the active material in many cases are covered with some sort of packaging, some sort of layer that can protect the active material. So I have crushed the sensor. Now you can see inside the sensor there is a shiny material. This shiny material is basically, I think, manganese oxide. That is what they use for usual thermistors. And then these manganese oxide is corrected with a, say, I think it's an stainless steel wire or aluminum wire. Okay, that acts as an electrode. Now let us see how this electrode looks like. So this is the electrode, and that is how they integrate the electrode with the active material. In most of the cases, thermistors are made of metal oxides. This can be nickel oxide or manganese oxide. I think in this case it's a manganese oxide thermistor, and then they cover the entire active material with some protecting layer. We call this as packaging. So packaging is a different aspect. Again, I'll not discuss the packaging aspect in this particular lecture, but just to give you an idea, I'm showing it. Now let us, this is more or less how it looks. It has an envelope that is a protective layer, and then you have a sensing element. As I said, this can be a metal oxide in case of thermistor. And let us now see the microscopic image of this sensor. Now if you put that crust or the broken thermistor under microscope, it looks something like this. So because the surface is very rough, it's very difficult to actually focus the entire surface in one go. That's why you may find that some portion are focused and some portion are like out of focus. But this shiny material is the active material in this case. Okay. Now if you look at this video, so this area is basically the protective layer, and then from here the active material starts, and this shiny material is the active material in this case, which is responsible for temperature sensing. And then you integrate the metal wire with this active material so that you can extract the electrical signal from that active material. So this is basically a two electrode sensor that has uh, a metal oxide as an active material. Okay. So in this case, the sensor that I've shown is a thermistor, and the sensor response is something that I've shown over here. We call it NTC thermistor, that is negative thermal coefficient. So negative thermal coefficient meaning that if you increase the temperature, the response or resistance of the sensor will decrease. Okay. And then you will also find another thermistor which is PTC, that is positive thermal coefficient. In that case, the resistance of the sensor will increase with temperature. But the thermistor that I've shown in the video is basically an NTC thermistor. So let us see the response of the sensor just using a very small experiment. So I've taken the thermistor and I've connected this thermistor with multimeter. So it will show you the base resistance at room temperature, which is 9.2 kilo ohm. So usually it's basically a 10 kilo ohm resistor. And the moment you touch it, the resistance decreases, because when you touch it or grab it, the temperature around this sensor will increase. So the resistance will decrease. Now, the moment you remove it, the temperature is again coming back. So it's kind of recovery. It's going back to its original or base resistance. Okay. So this is a simple experiment associated with the temperature sensor. Then I'll show another sensor which is known as light dependent resistor. So it's an optical sensor. The sensor structure is uh, shown here. So it has two electrodes, two metal electrodes. These are like interdigitated electrodes. So this silver colored thing is the are the electrodes, and each of these electrodes have different tip kind of structure. So we call it interdigitated structure. And the serpentine kind of structure is the active material. In this case, the active material is cadmium sulfide or cadmium selenide. Then you connect this metal wire with cold welding. So these metal wires are connected with the metal electrodes shown over here using a cold welding. So when this sensor is exposed to light, the light will interact with this active material. The material is here in this serpentine channel, and then it will create or generate excess carrier. That excess carrier will reduce the resistance of the sensor. So this is again a resistive type of sensor. Let us see the video of the sensor. That is how it looks commercially. It has a ceramic base also. So this is a ceramic base. On top of that, there is a thin film of active material. Usually it's cadmium sulfide or cadmium selenide. And then on top, you'll find these electrodes are there. So these silver colored things are actually electrodes. Then you connect the electrode with two metal wires using a cold welding. Okay. Then there is a protective layer also. On top of that, you put a polymer layer to protect the active material from other environmental conditions. So there is a thin protective layer, transparent protective layer. Okay, on top of this sensor. So this is how it looks like. If you put that sensor under microscope, it will look something like this. So this area is the electrode area. This is the metal wire that has been welded, cold welded with the electrode. And this brown area is the active material. Okay. So when we are focusing and defocusing, you can see that there is a layer also on top. Sometimes the objective get focused on the top layer. There is a transparent layer on top. That layer is a protective layer. So it protects the active material from the other environmental conditions. So this brown area is basically your active material. It's either cadmium sulfide or cadmium selenide. So that is how a light dependent resistor actually looks under the microscope. So again, we'll do the similar experiment. So if you connect the sensor with multimeter, now the sensor is exposed to light, so it will give you certain sort of resistance. So if you connect it, then you'll get some resistance which is around say 6.5, 6 point or 7.5 kilo ohm. The moment you put hand on top of it, then it's a dark condition, so it goes up. But the moment you remove the hand, it's again back to say 6 to 7 kilo ohm. So you have to make sure that these two electrodes are not touching with each other. In this case, these electrodes are touching. That's why you get a zero voltage, or sorry, zero resistance. Okay. The moment you put the multimeters correctly and then you put the hand on top of the sensor, it goes up to 60 kilo ohm in the dark condition, because now the light is not interacting with the sensor. The moment you remove the hand, it comes back to say 7.4 kilo ohm again. So it's the when the sensor is exposed to light, then the resistance is less. The moment you put the hand, the sensor is not interacting with light. You can consider this as a dark condition. The resistance goes very high. This is another sensor which is a multi-sensory system, I would say. this particular sensor has a humidity sensor and temperature sensor connected to it. We call it a sensor module. It's not a single sensor. Basically, this also has different other components you can see over here for signal conditioning. So it has two sensors. One is humidity sensor, another one is a temperature sensor. The temperature sensor used in this module is a thermistor, and the humidity sensor used in this case is a capacitive humidity sensor. Okay, and the entire thing is a sensor module which has three terminal ground, VCC for supply, and then you have a data terminal as well, which provides you the analog signal from those sensors. So you can extract the signal from the data terminal. You can put that into the next level of system in order to do further analysis. So this is a capacitive humidity sensor example. So under the microscope, the sensor looks something like this. So it's a very tiny sensor. The image is shown on the inset here. You can see it's a very tiny sensor, maybe 2 mm by 2 mm. It has three layers. This is the top electrode. It's a kind of porous electrode. Then you have an active material. You can see the green portion is an active material, and this is the top electrode in higher magnification. Then you have these wires that you have bonded with the sensor to extract the data. So this area is kind of the active material. Then you have top electrode, the golden area, which is kind of porous, so that water molecule can interact with the active material. And then you also have a bottom electrode. So see the bottom electrode, we have destroyed the sensor. Now you can see the bottom electrode is made of aluminum. This silver colored thing is the bottom electrode. The middle one is the active material, and the top one we already have seen. This is the top electrode. So that is how a capacitive sensor look like. I mean, there are different geometries associated with capacitive sensors, but this is one of them, just to give you an idea how a sensor actually looks like. So I've put this uh, sensor with you. Just a minute. I think there is some issue with the presentation. Give me some time. I'll restore the presentation again. By the way, if you have any queries, you can ask me. Meanwhile, all right, I think it's okay now. So, yes, I think you'll be able to see the presentation now. So we already have seen the videos. Let me check. So let me show you another video. This is again a module. This is a IR sensor module. So you have a IR source here and IR detector here. The black one is the IR detector. Then you have different other components present over here. These are for signal conditioning. So we call this sensor module, and you can apply this particular sensor module for various other applications. Okay, so this is how it looks like. Similarly, if you look at the SMD components present on a sensor module, so what I've done is I've taken an SMD component and put this under microscope. So you can see how tiny these materials are. So these are the interconnects. So one has to also check the interconnects very carefully. Sometimes your interconnects may break and the entire sensor module may not work. That is how it looks. So these are the ICs. This is the dot on the IC. This is the inset image you can see. This is the interconnect. These are all SMD components. SMD means surface mounted device. So you can mount them on the surface. These are the tiny version of usual components. So these are, for example, the resistors. So the resistors look very small actually in SMD component. Now let us start our discussion why we need sensor. So as I have said that sensors can be used for environmental, healthcare, agriculture, assistive technologies, and automobiles. So you need sensors for various applications. In fact, if you take an example of your smartphone, the smartness of your device is associated with the sensors. Higher the number of sensor, smarter your device will be. For a typical smartphone, you will find that there are at least say 9 to 12 sensors present in the smartphone, and that is responsible for the smartness. So even nowadays, you'll find different smart gadgets, for example, smart AC, smart refrigerators. In all these cases, the sensors are there in order to make them smarter. So basically, sensors in those cases take feedback from the surroundings and then tell the processor what to do next. Sensors has a huge application in robotics because the entire robotic division depends on the feedback or control. The control is again area which requires a lot of sensing arrangement just to get feedback, because without feedback most of the controls are not as good as it is today. So that's why we need sensor in many places, and it also makes the life of a sensor engineer very difficult because it's highly interdisciplinary. When you start working with sensor, you should know a bit about biology, a bit about chemistry. If it's a chemical sensor, then you should know the chemistry. Even if it is not a chemical sensor, just to fabricate those sensors, you should know certain chemistry aspect of it. And then you also should know a bit of biology. If you are working with biosensors, you should know electronics, you should know electronic devices. Inside electronics also, you should know electronic devices, electronic controls, feedbacks, to make the system properly suitable for the sensors. So a sensor also comes with the system associated with that, because once you develop the sensor, you also should know what circuit you should make in order to make that sensor work. Otherwise, only sensor is not sufficient for any application. Okay. So today, from this slide onwards, I'll first discuss what is the requirement of sensor in healthcare application. I'll take one healthcare situation in particular to give you a idea, and then we'll go through very briefly a research problem related to sensor development. So how we can develop a sensor for a specific, say, healthcare application. Now I have listed some of the diseases that are very common and some are actually very prevalent in our country. So if you look at the slide, you'll be able to understand that there are many different diseases, right from cardiovascular diseases, stroke, tuberculosis. COVID-19 is something that recently has come up. Then vector-borne diseases like chikungunya, malaria, then cancer, of course, then chronic obstructive pulmonary disease, that is disease associated with lung because of unhealthy environment, polluted environment. This is a big issue in bigger cities, for like metro cities like Delhi, Bombay, Kolkata, Chennai. Everywhere the pollution rate is quite high and it's alarming, so COPDs are increasing day by day. Then you have different other diseases like diabetes, liver cirrhosis, and so on and so forth. These are the 10 most common diseases in India. And you'll find there are some diseases that are very much prevalent. For example, cardiovascular diseases, stroke, then TB. These are the one of the most prevalent diseases in the country. So in order to reduce the prevalence, one should have a very portable device that can detect the cardiovascular diseases, that is heart diseases or stroke, at a very early stage. If you can develop something of that sort, then definitely it will be helpful. That is what we come up with after discussing with, say, doctors, names, and other medical organizations. But the problem is when you develop those technologies, that has to be affordable. If you make a device which is, say, 20,000, the cost is 20,000, then it doesn't, it will not serve the purpose. You need devices, say, costing 100, 200 rupees, so that everyone can procure that device and can use it to monitor their health. One of the success story in this direction is the EcoCheck, that is the blood sugar measurement. Nowadays, you'll find blood sugar measurement device in various places, and you get the result, preliminary result, maybe in 5 minutes. Then you can go to uncentralized facility in order to do further testing. But the thing is, until and unless you have a device that can give you an initial indication, it's very difficult for everyone to go to a centralized facility like pathologies, hospitals, and then get themselves checked for certain disease. So in this direction, we have chosen the cardiovascular disease or stroke. If you look at the statistics worldwide, it's 17.9 million people dying with cardiovascular diseases per year. 75% comes from low and middle income countries, like developing countries like India and Asian countries. And out of that, 85% are the victim of heart attack or stroke, which is commonly known as heart attack. So if we can make some device that can provide us an early indication, then it may serve the purpose, and that also has to be large scale deployable. We can't make something which is not deployable or which is not large scale deployable. Even today, I think more than 70% of the population stays in different rural areas or suburban areas, and they have very limited purchasing power. So when you come up with a solution, at least for the countries like India or any developing or developed countries also, uh, you need to come up with a solution that are affordable. Otherwise, it will not make any sense in the context. And if you look at the heart diseases, we probably have most number of medical developments in the area of cardiovascular diseases. You have nowadays angioplasty, you have cardiac ablation catheters, you have AEDs, you have pacemakers, you have implantable uh, defibrillators, you have prosthetic heart valves, you have stents for heart diseases. But the mm, issue is most of these devices are quite expensive and maybe out of the reach of most of the population that are staying in this country. The idea is whether we can make some affordable solution to that or not. With these particular solutions are so expensive that, and at the same time they are centralized. You have to go to an hospital. That 90% of the victims usually don't go to these solutions until and unless the problem is chronic. They initially tend to ignore the problems, and then they go to the doctors for further treatments. But what we want is to develop certain sort of solution where they don't need to wait for a certain amount of time because of, say, financial issues, time issues, or whatever it is. So in that case, what we are trying is we are trying to develop some sensors which can detect, say, preliminary data associated with heart. So I've listed down some of the heart parameters associated with cardiac diseases. For example, heart rate, pulse pressure, heart sound, pulse timings. These are the very basic parameters which will get influenced at the very early stage of your disease. Then there are tertiary level medical facilities like electrocardiogram, echocardiogram, angiogram, chest MRI. These are the solutions that are really expensive, and people usually do this when the situation is not in favor. And then, of course, you have blood test. But if we can cater to these first four parameters, we actually can provide certain sort of initial indication or awareness as far as the heart disease is concerned. I have given a representative figure here. how early diagnosis may help. For example, if it's a cardiac problem or a cardiovascular problem, it's basically a lifestyle dependent problem. So the problem will gradually increase, and then a person will start treatment, say, after 45 years of age. And then the treatment goes to the tertiary level testing where you need a lot of money. However, if you can diagnose the problems at a very early stage, say between 20 to 30, then probably just by changing the lifestyle, you can bring that problem down so that you don't need a tertiary level solution after 45. Currently, we don't have any solution to that. That's why people wait till 45 when the problem becomes very high, or it becomes very chronic. Then only they go for a help to different doctors. Usually symptoms progresses, say, after 45. Before that, the symptoms are mild, but just by looking at these parameters, one can diagnose the progress of this situation very precisely, and they can actually change their lifestyle to bring things into normalcy. So in that case, if you want, we have targeted two different parameters: heart rate and pulse pressure. So heart rate is an electrical activity. We can measure that using radial pulse and carotid pulse. So radial pulse is like measuring the pressure from your hand. So you, even if you place your fingers on top of the radial in your wrist, you'll get the radial pulse signal. And then you also can get a carotid pulse over here near your neck. So these are the things that may help us to get the heart rate. At the same time, you can measure the pulse pressure from radial and carotid pulse. So we have now two objectives: one, to development of a pressure sensor, because anyways you need the pulse pressure signal, and the second is the calibration of the pressure sensor for this particular purpose. So these are the solutions that we may look into. We can develop piezoresistive sensor, we can develop capacitive sensor, we can develop triboelectric sensor, piezoelectric sensor, magnetoelastic sensor for these purposes. So what we are relying at this particular level is the piezoresistive sensor that I'll discuss in the coming slides. But apart from that, you also have various other options that you may choose. But let us start with the very basic type of pressure sensor and see whether we can get certain sort of advantage from that piezoresistive sensor. One of the major reason behind choosing piezoresistive sensor is the cost associated with the fabrication. Usually resistive sensors are relatively affordable than other type of sensors listed over here. Now, as we have already discussed, what type of sensors we are going to we are going to consider in this case. So in this case, I'll discuss mostly a pressure sensor. And when it comes to pressure sensing, then again we need to develop some sensor at a low pressure range, because anyways radial pulse and etc. will come into a low pressure range. And usually in the low pressure range, the of limit and sensitivity both are low. And if you move to high pressure range, then your limit and sensitivity is high, because it's quite intuitive also. If you have a pressure sensor, if you press it more, definitely you'll get a high limit, at the same time higher sensitivity, because applied pressure is quite high. But if the applied pressure is very low, in that case, achieving higher sensitivity is an issue. Usually for low pressure range, you get a very low sensitivity. However, in this case, what we will try to develop a pressure sensor that has a, say, limit, considerable amount of limit, at the same time high sensitivity as well, so that we can apply it for the radial pressure measurement. So to achieve that, what we have done is we started with a microstructure assisted pressure sensor. So in this case, we have taken a substrate that is PDMS. It's a polymer substrate, again a flexible substrate, and it has an active material P.PSS. This is again a very stable conductive polymer. And then we made aluminum electrodes as it is shown over here. And then there are metal contacts in order to connect the sensor with the system. So we have now a substrate with microstructure, and then an active material of P.PSS, which is again a polymer. Now both these materials are flexible. So It's like a paper. You can bend that particular material. This is how the electrical response, uh, you know, structure is. So because you have microstructures, so when these microstructures come into contact, the moment you press it, the interface resistance will change, and that will lead to a change in the overall resistance of the system. So if you look at this particular structure, this is a magnified structure of a section of the sensor. So microstructures are there in the sensor. So there are maybe lot of microstructures present. What we are doing here is considering only one microstructure present over there and trying to analyze the theory associated with it. So you have a top surface made of PDMS, then you have PDMS microstructure, and on top of this microstructure you have P dot PSS, that is the active material which is conductive in nature. So you have R1 resistance associated with the microstructure. Then you have an interface resistance, because when two materials touch each other, then in the interface also you'll find there is a resistance. We call it interface resistance. Now, the moment you press from the top, this interface resistance will change. Here, the calculations are given. I'm not going in details of this calculation. And then accordingly, you can actually calibrate this interface resistance with the applied pressure. We did a simulation also. This is a stress strain density function simulation, a bit complex, not needed at this stage, probably. Just to give you a understanding, I'm showing that this is a stress strain density function which we have taken just to measure the stress and strain associated with the PDMS structure, and then we solve this for this stress equation in terms of extension ratio. Extension ratio is nothing but the deformed structure divided length of the deformed structure divided by original structure, which if you do calculation, it's nothing but 1 plus strain. So it's the indication of the strain applied. These are the simulation model that the governing equation associated with it. We used AC/DC model because there are electrical signals associated with that. We also have used linear elastic material model and hyperelastic material model in this case. Again, not needed, just to give you a basic idea, just in case you feel interested, you can go through the paper that has recently been published. And then in the simulation, you'll get the response, that is the delta R by R0 with the applied pressure, how it changes with applied pressure when you vary the microstructure dimension as well as the thickness of the substrate layer. So what we figured out is 500 micrometer for 1 mm thickness substrate is the best possible combination. So that is how you can develop the sensor. We did this with micro fabrication technique to some extent, and then we also used replica molding technique in order to develop these microstructures. These are optical microscope images. So you can see the microstructures, how it looks like, and the moment you put the active material, what is the surface of the sensor. So the scale bar in this case, I guess, is 50 micron or so. This is how the device looks like. You have electrodes, you have PDMS substrate, and this is the FESM image, that is field emission scanning electron microscope. And then you can see how these hemispherical microstructures look like. This is the first hemispherical microstructure. Then this is the porous hemispherical microstructure. So we actually made this structure porous with a different process that probably I'll discuss. And the moment you put the active material P.PSS, this is how it looks. Okay, so the corresponding high magnification images are shown at the bottom in the second row. These are the sensor responses with hemispherical microstructure. So you can see that the applied pressure till 0 to 8 kilopascal, the 500 micron structure gives a sensitivity of 0.07 kilopascal, and for 500 micrometer or 100 micrometer microstructure thickness, microstructure diameter, it gives a sensitivity of 0.05 kilopascal per to the power minus 1. So it's like 0.05 per kilopascal. So that is the response, which again is not sufficient for the application that we have targeted. So that is why we went with the porous hemispherical microstructure, and finally we got a device like this where the sensitivity could be improved till 9.51 kilopascal per kilopascal. So previously it was in the range of 0.07. Now it's almost 9.5. So it's order of magnitude higher than what we got without porous structure. So we are applying the entire sensor in this domain only between 0 to 10 kilopascal for our application. This is a comparison table, which again is not very important. So that is how the system looks like. So we developed this pressure sensor with entire electronic circuitry. The moment you put it on the wrist, you get the sensor data or heart rate data at the same time, pulse pressure data as well in a mobile application. So if the work is still in progress, so that we can make it even better for a large scale application. This is the heart rate detection data. Again, I'm not going in details to this particular slide. The idea is to use the system for heart rate as well as pulse pressure. We took this further in order to develop a better system. So in that case, what we did is like we tried to make molecular crystals made of small molecules, 4CFNCS, and to harness their plastic deformation at various bent, twisted, and coil structures so that we get a high sensitive sensor. So the try was not successful. The kind of experiments that we have done was not successful because we could not achieve higher sensitivity that we could achieve without this structure. But anyways, the work is still in progress. In this case, the sensitivity is 0.2, which is definitely higher than 0.07, but again lower than 9.5. So we are still working on it in order to develop even sensitive sensors. In this case, we took microchannel based geometry. So this has been covered by different national medias as well. So far, what I've shown is a research related problem, so that you also get an idea how a research related problem will look like when you start working with, say, pressure sensor. Now I will quickly browse through various other sensor examples that we have developed. So for example, say temperature sensor, pressure sensor, strain sensor, biosensor, and microfluidic sensors. So these are the sensors that we have developed. We also developed a kind of sensor that can be attached to mask. This is a micro droplet based sensor system, how it looks like. We also developed a sensing antenna where the antenna itself can work as a sensor. And then there is a smart bandage that can actually transfer data associated with a wound to a mobile application. The idea is again to come up with solutions that are large scale uh, deployable, so that we can deploy it in a rural setup as well, low income setup as well. So how to make these sensors deployable at large scale? One solution is to develop microfluidic sensor, because in that case the fabrication cost is comparatively less, and then to develop flexible sensors, because again if you use a flexible substrate other than a silicon substrate, the cost reduces significantly. Usually silicon substrates are quite costly. For each silicon substrate you need to spend say 10,000, 15,000 of rupees, and then the fabrication process again is very costly. So here is an example of a micro droplet based amylase sensor. I already have discussed that there is a difference between solid state sensor and liquid state sensor. The sensor I have shown before is a kind of solid state sensor because entire sensing mechanism was performed in a solid state. And now the example that I'm showing is a liquid state sensor. In this case, we are taking the we are actually considering a micro droplet as an active material to detect amylase. Amylase is an enzyme that is present in the blood. If the concentration of amylase is higher, it indicates pancreatitis, which is again, kind of prevalent in many locations in the in our country. So that's why we started this project, and we tried to come up with a solution which is low cost, you can understand if it's a droplet based solution, then you don't need to worry much about the deposition or fabrication of the active material on the sensor, which usually again is costly if you go through microfabrication. So in this case, what we have done is we have uh, put a droplet on top of a substrate, and then we applied heat underneath. Now, because of that heat, you'll see some recirculation in the droplet. Now, this recirculation attributes to two different phenomena. One is thermal convection. The moment you, for example, if you take a bucket or container with water and put it on top of a stove, then because of heat, you'll see there is some recirculation in that container, recirculation of fluid, for example, water in that container. That recirculation leads to thermal convection. Usually, those recirculations are random, not very organized. And if you put that droplet on top of the heated substrate, because of heat, because the temperature near the substrate will be very high comparatively if you compare the same with the top of the droplet, which is cold. Because of that temperature gradient, the surface tension also changes. Now, if the recirculation is based on surface tension, then you will find that there is an ordered recirculation inside the droplet. So that is known as Marangoni effect. So we took advantage of that Marangoni effect. We put an salt solution so that the solution is conductive. Then we put starch on top of it, which reacts very specifically with amylase. The moment you put blood amylase onto it, the starch reacts with the amylase. They form an complex. They actually breaks down the starch into smaller molecules. That leads to a high amount of electrical current across this if you put a bias, and then that you can calibrate with the amylase concentration. So here again, the simulation study is given. How the recirculation will look like? Probably it's not that clearly visible. The recirculation images. So you can see for delta T equal to 10 degrees centigrade, the thermal Marangoni is quite strong in comparison with natural convection. And if the delta T is 50 degrees centigrade, then natural convection takes over. The moment you get a natural convection which is taking over the thermal Marangoni effect, then the entire process becomes random, which is not the kind of target of this study. So we kept delta T, that is the temperature difference, to be 10 degrees centigrade in this case. These are some of the analyses. You can see the sensor that we have developed. These are basically two electrodes that we have developed on a flexible substrate, polyimide substrate. And then we put a droplet on top of these sensors. So these are arrays of sensors. You can put the drop on top of one sensor. This is the microscopic image of the electrode. The moment you put the drop on top of the sensor and then you heat it, then you add amylase on top of that droplet, then it will give you some response in terms of concentration of amylase. Higher the concentration, higher will be the response. So these are the calibration that we have done. This is the system associated with it. This is how the system looks like. So it's more or less 50 mm, that is 5 centimeter by 2.5 centimeter, not very big. And that is where your sensor is. So you put the sensor here, put the droplet, and you take the measurement. That is how the measurement looks like from the PCB itself. So in this case, uh, we could pull up the or pull through the detection. However, as far as the device is concerned, it's not very convincing because liquid state devices are very unstable when you put it in the ambient condition. However, our target is to also develop a device structure which is good enough for large scale deployment. We are still working on it as far as the device is concerned. But as far as the sensor is concerned, it works very fine in the laboratory setup. In a ambient condition, we need to check how we can get rid of ambient influences. Okay, now just to make things more stable on a wearable setup, we also developed a stable substrate based on multi-layer. This is just to give you an idea how substrate also may affect the sensor performance. And this is the structure where we used a concave structure in order to increase the device stability on top of the substrate. This is another example of unprinted chipless temperature sensing antenna, and this in this case the antenna itself can detect temperature. We don't need any separate sensor. The sensing element is put on this loop antenna, and then the sensor itself can, the antenna itself can detect the sensor. This is the smart bandage that we have developed. This is the system associated with it. So if you put that smart bandage in any of the wounds, it will be able to give you the temperature, strain information associated with the wound just by analyzing the temperature and the strain around that wound. We'll be able to get certain sort of idea regarding the wound healing process. We are integrating more sensors to it to make it more, uh, applicable for this medical purpose. This is my team members who are involved in various activities that I have shown over these slides in the past one and a half hour. But and then we thanks to the collaborators also for all these works. They are the collaborators, and I got financial support from various funding agencies. I've acknowledged them over here. But before I close, I would like to give you a video tour of some of the laboratory setup that we have here. Let me check if we can play that video here or not. I have, I think, 15-20 minutes more. The video is 10 to 15 minutes. I'll put it in the fast forward mode. Just a minute. But if you have any queries, you can ask. Yes, I think this should be visible. If it is not visible, let me know. So, so put it a bit of fast forward mode. I'm not sure if you can hear the music or not, but it doesn't matter as long as the video is visible. Pardon me if it is not playing in the middle because of the issue. These are the basic labs in here in the biology and chemistry department. As I've said, that sensor is an interdisciplinary work, so you may need help of biology and chemistry. That's why you can see a lot of collaborators. And these are the typical laboratory setup where maybe biology and chemistry works has to be carried out. So this is a microscope by which you can see different biology or chemistry. This is an animal facility. So sometimes we work with different animal models as well. So these are specific kind of labs. Some of the characterization facilities. So this is an plant growth facilities are biofacilities. In chemistry also you have various other facilities for synthesis, characterization. Again, these are for undergraduate labs, but some of the experiments we do here also, which are very basic, for example, some synthesis and etc., so that we can develop different materials for our sensors for in the flexible electronic applications. So these are the common instruments. Loom, these are the few modes. So few modes are usually used to do experiments that actually issues out some volatile organic compounds not good for health. So it has to be performed inside of them. These are the microscopes. So we have different types of microscope for characterization, upright and inverted. For example, if you do a microfluidic experiment, you may need an inverted microscope. So in that case, you have to do your samples to an inverted microscope. These are some of the rock facilities in our environmental science. So they study different types of rocks in order to extract minerals from there. Uh, as a sensor researcher, we also try to develop sensors for various environmental applications. We work closely with them as well. These are the physics labs. Some of the equipments are very useful for sensors. They have different set of equipments for their UG studies, but uh, usually most of these equipments are not needed for sensing experiments, but some of them are. The standard equipment in electrical engineering. There are some of the kits for training purposes, some of the magnetic experiments. There are some of the facilities, including 3D printing facility and the oven and the furnaces. This is again a different kind of microscope. This is some facilities in our chemical engineering department with the furnace, and then you have various other equipments for synthesis with the UTM, which helps in characterizing mechanical properties like stress, strain, elastic modulus, and so on and so forth. Then globe box. So globe box are usually used to do experiments in a controlled environment. These are the standard chemical engineering equipment for the UG lab activities. This is an electrospinning machine that we have. This is a spin coater that is available in my lab. There is a 3D printer as well, which is not visible. These are basic synthesis areas, which is PCB making facility, probe, fume hood, optical microscope, the UV visual spectroscopy, the vacuum oven, and tubular furnace, the electrical setup, electromagnet, LCR meter. This is a multi-robot owned. It's a robotic facility where we do robotic experiments. You can see small drones and how they track the trajectory of different robots in here. These are the electrical probing system where multiple probes are here in order to probe a single device. This is a CAD tool. We have a vacuum probe system as well. Then basic lithography system, fume hood. This is something we have developed here for optical measurements. These are CIF facilities, full instrument facilities, with NMR. NMR is basically used for um, different chemical chemical detection purposes, maybe bond energy or something. I'm not an expert of this, so I'm not to comment on the working, but usually for chemical composition, if there are single bond, double bond, carbon, etc., these information they may get from NMR. We don't need this facility. This is an efficient facility that we usually use got for our measurement. These are the mass facilities. So this is the TG analyzer. These are the laser facilities. We have Raman spectroscopy as well. I think the one behind is the Raman spectroscopy. Then there are other laser facilities as well. These are XRD facilities for material characterization. We get crystal structure and information associated with crystal structure with XRD. Then we have central computer system as well, which other places. But we have some sort of softwares, for example, ATK, Atomistic Toolkit. We have console. We have Coventerware, then CAD tools. So with this, probably you would. So that is. I'll go back to my presentation.
Yes, I'm here. So
Yes.
thank you, sir. Thank you for sharing your knowledge with us.
You can call me Mitradip, not issue.
Sure. Yeah. If anybody has any question, please you can ask.
So just all of your information, Priyansha and we did BTech together. So she is my batchmate only. Yeah, somebody was saying something, please.
Anybody has question?
So I'm also floating. Just would like to take this opportunity to say that I'm also floating a course in NPTEL that is related to sensor technologies. Just in case if you are interested, you can join this course. The enrollment will start from 22nd May. Yeah.
So I think there is no question, or they can mail you also if they
Sure,
have
sure.
any
Not
queries.
a problem. Not a problem.
I will share the mail ID.
Sure, sure, sure. Not an issue. Okay. Thank you very much for calling me, Priyansha.
Thank you.
Thank you. Thank you very much. So I'll take a leave now, I think.
Yes, yes, sir.
There's nothing. Oh, don't call me sir. You call me
Yeah,
Mr.
yeah. Yes, Mr. You can leave.
Okay. Bye.
Okay, so our session is ended here. Tomorrow we will again meet at 2 p.m.